And that brings us to now let's have a look at how we would rotate an area that's in between two curves around either the x-axis or the y-axis. Now it's quite straightforward. All we need to do here is really just substitute one volume from the other. So you can do them separately and just subtract them, but if the bounds are the same, then you can put them both into being the same integral. So an example here, if we're rotating this orange shaded area here around the x-axis between the bounds a and b, clearly you might have to find b, so that's a little complication. You might need to find the intersection of the curves in the first place, or they might be given. But basically you want to just have a look at which is the upper curve in that interval and which is the lower curve. Because if you imagine rotating this green line here around the x-axis, you're going to have a larger solid, and when you rotate the blue line around, you're going to have a smaller solid, and you need to take away the small solid from the large solid to see what's left. You're basically going to have sort of a donut shape, if that makes sense. So instead of doing them separately, which you could do, you can take a bit of a shortcut and say we need pi, and then we need the upper curve, or the bigger one, squared minus the smaller one squared dx. So that's quite straightforward, and clearly here we're just saying that y2 will be bigger than y1, which is greater than 0. And if you're rotating around the other way, it's the same, except with x where the y would be. And you need to think not which one is taller, but which one is further to the right, because that will be the big one. So here, imagining rotating this blue line around the y-axis, we're going to get a larger solid, and then we need to subtract what we get when we rotate the green one, and we'll again end up with a donut sort of shape, which we can find all in one go because the bounds are actually the same. And again, you might need to find those bounds if it's an intersection point, or they might be given to you. All right, this example will give us a chance to practice rotating a shaded area around both axes. Now, a bit of work to do before we start. We don't know what our bounds are. So let's just first consider that when x equals 0, we can sub it into either of these and see that y would be 4. And when y equals 0, 2x is 4, so x equals 2. So let's do the x-axis first. Start by writing your formula. The volume equals, now our bounds are 0 and 2 because we're rotating this around this way, so we've got horizontal bounds. And then our formula says we've got pi here, although we could bring that out on the next line, and we need, start by just writing the basic formula, y2 squared minus y1 squared dx. And then on the next line, put in your specifics. At this point, you might like to bring the pi out the front. Now, y squared is going to be all of this squared. 4 minus x squared squared minus 4 minus 2x squared dx. Now, you can see here, I don't really need brackets around the whole thing, but obviously I need to tidy up my whole integrand before I'm ready to integrate. Get it as simple as you can. So that gives us, what do we have here? We'll expand this out. We've got 16 minus 8x squared plus x to the power of 4 minus, now I'll be careful here and use brackets, expanding just this part, I've got 16 minus, what's that, 16x plus 4x squared dx. Now you could do some of your tidying up on the side and then throw it back in, up to you how you want to set it out. There's a bit of choice there. Now I've got 16 minus 16, so those are going to go, and I've got x to the power of 4, that's my biggest power of x, so I'll write that down. And I've got minus x, 8x squared minus 4x squared, so that gives me negative 12x squared. And the only term left is we're taking away negative 16x, so we're adding 16x dx. Okay, a bit of work to do there, but we're getting there. All right, next we can integrate. So we've got pi, and then we've got our large brackets, and we have x to the 5 on 5 minus, here I need x cubed, and when the 3 comes down, this will need to be a 4. Just always check that your term differentiates back to get where you need to. And this is x squared, which means this needs to be an 8. And I've got my bounds of 2 and 0. So on the next line, I've got pi. This is getting a little bit messy, but we'll proceed. We've got 32 fifths. I might just change it to a better pen. 32 fifths minus, what's that, 4 eighths, which is 32, plus 8 fours, which is plus 32, minus, and then this is going to be 0 minus 0 minus 0. So we've just got 0 in there. Okay, the 32 and the 32 are going to go. So we ended up just with, as our final answer, I'll just write it on the side here, 32 pi on 5 cubic units. So that's that one done. And now for the other one, we'll need to consider different bounds this time. Let's just go with the black pen. We've got, our bounds are going from 0 to 4, and I'm going to write the pi in, and then we need x squared, x2 squared minus x1 squared dy. Now, a bit of working on the side perhaps might save me from having to do a lot of my simplifying over here. So let's use our different coloured pen and do some side working. We need to get this in terms of x. So if we've got y equals 4 minus x squared, then x squared is equal to 4 minus y. Now, we don't need to get this in terms of x and then square it. What we actually want is x squared, so this is perfect. So on the next line here, we can say, actually, let's put our pi out the front at this point. From 0 to 4, we need 4 minus y. And now for our other formula, we have y equals 4 minus 2x. So that means that 2x equals 4 minus y. X equals 2 minus y on 2. And that means that x squared is going to be, we need to square all of that. So there's a little bit of work to do here. 4 minus, now we need to multiply them together, that's minus y and double it, minus 2y plus y squared on 4. So we need to sub all of that in over here. So I think you can see doing a bit of the work on the side sometimes just saves you a little bit of a headache with your setting out. So we need to subtract all of that. Now, careful not to make a sign error. We're taking away 3 terms. Let's just write them in exactly as they are, and we can tidy it up on the next line. And we need dy in there as well. Okay, a little bit messy. Luckily, I've got a different coloured pen. So your side working, obviously, you'd have a bit more room on your page than I've got. So now let's tidy up our integrand. We've got 4 minus 4, so they're going to go. And we've got minus y plus 2y, don't make a sign error, so that gives us y. And we've got negative y squared on 4 dy. All right, now we're ready to integrate. So square brackets, we get y squared on 2 minus, let's call this y cubed. The quarter will come along for the right, and we need to divide by the new power, so we get on 12. Now just always double check when you integrate that it differentiates to get back. So the 2 will come down, yes. The 3 will come down and we'll have a quarter, and the 3 will drop to a 2, yes. Okay, now we're ready to sub in, and we get pi. 4 squared is 16, divided by 2 is 8, minus 4 cubed is 64, divided by 12, that's 32 over 6. Let's call that 16 over 3. Again, you can put this into your calculator if you want to, minus 0. All right, so we've got 8 minus 16 thirds. That's 24 thirds minus 16 thirds, that's 8 thirds. So we end up with 8 pi on 3 cubic units for that one. Now, one final consideration, you've often got 2 choices if you're rotating a region between curves, and one of those curves is actually a straight line, a horizontal or a vertical one, depending on which way you're rotating. So in this example, if we're rotating this around the x-axis, then we could say that what we've got is from our lower bound to our upper bound, sorry, that was a bit of a weird squiggle, we've got pi, and then we've got, in brackets, 5 squared, because this is the line y equals 5, minus all of this squared, like that, dx. Now, one small problem with all of this is that, okay, we need to expand this out, but there's also potential for us to make a sign error doing it this way, because we've got our upper boundary here minus the lower one. Can you see an easier way that we could do this? Well, what's going to happen if we rotate the upper curve, which is just a line, around the x-axis? We're just going to get a cylinder. So if you want to, an alternate working, which might lead to less mistakes, is that we could actually just say we've got pi times 5 squared, because pi r squared h multiplied by 1 is just the formula for that large volume that we're going to get. And then that's got no integral in it whatsoever. So we can see that on the next line, that's just 25 pi. And then we could subtract, and now we're just finding a nice simple integral, and it doesn't have that subtraction in it. And we need to just do the 3x squared plus 2 all squared dx and multiply that by pi. This is alternate working, and it just means that your integral might be a little bit simpler and maybe there's less chance of making a mistake. On the other hand, I suppose you're still subtracting a whole lot of things. Another way again that you could go so that you've got less chance of making a sign error would be to say volume 1 equals, and literally just come up with that using this working. And then volume 2 equals, now we're not subtracting anything, we're literally just finding all of this separately. And then you could say volume 1 minus volume 2 at the end. So that alternate setting out would only really be recommended if you're making mistakes with your signs. There's always another way to go.